All right, now that we've talked about areas, let's talk about finding the volumes of a solid. Now, we've found volumes of things before, things maybe even as simple as some kind of rectangular box. And we know that to find the volume of that, you just take the length times the width times the height. And that's what you got for the volume. Well, we're going to be finding volumes, but of irregularly shaped items. Maybe like this blob right here. Let's think of this blob as a loaf of bread. And what we could do, what they show in this first drawing here, is we could slice the bread. And even in the second drawing here, they show let's slice the bread, but let's give it some thickness. And if we can find the area of that slice of bread and multiply it by the thickness of the slice of bread, which they call delta x, an area, kind of like we did up here, where to find the volume of this box, when we took the length times the width, we really found the area of the bottom. And then when you multiply by the height, what you've got is you've got the volume. Volume is area of a slice times the thickness of that slice. We're down here, we'll find the area, and we'll multiply by the thickness, and that should give us the volume of that single slice. And if we do that maybe 1, 2, 3, 4, 5, 6, 7 times, and add those things together, well, maybe we get a pretty good estimate for the volume of the entire thing. So this is called volume by cross sections, because what we're going to do is we're going to make a slice. And that slice is a cross section of our loaf of bread or whatever we've got. And so we're going to find the area of it, multiply it by the thickness, and we're going to add as many of these regions together as we can. And the more regions we add together, the more accurate our estimate of this volume is going to be. So, to find volume by cross sections, we must slice, multiply the area by the thickness, and then add up all the volumes of the slices. And that's what this says. Add area times thickness. Now, the more of these that we can add together, the more accurate we're going to be. And that's where the integral comes in, because how many things can an integral add together? And hopefully you're thinking in your head, an integral can add an infinite number of things together. And so we're going to take the area times the thickness and starting at some value and ending at another value, we're going to add an infinite number of those slices together. An infinite number of these volumes will be added together to get the volume of the entire figure. So let's see how this is going to work. Suppose a solid has a circular base of radius 3, cross sections perpendicular to the x-axis are squares. Find the volume. Now, trying to understand what this thing looks like boggles your mind. Now, if you were in class, I've got an actual physical figure you can hold in your hand that has a circular base, but every slice of it is squares. So I'm sorry you can't see that today, and I'm sorry I can't show it to you. What we're going to do is we're going to draw a picture of this. Now this is the top view. As we look down on this figure, and we're going to put it on the XY axis, we're going to have a figure that looks like this. It's a circle. And the radius of this circle is 3. So it goes out here to -3, and it goes out here to +3, up to 3, down to 3 on the wall axis. What I'm going to do as I look down at this from the top is I am going to take my calculus Ginsu, and I am going to slice this thing. Take a very, very thin slice, perpendicular to the x-axis. And I'm going to take that slice, and I'm going to bring it over here, and I'm going to stand it up. So it's standing on edge, and again, I'm looking down at this from the top. There's my slice. Kind of like a CD standing on its edge. But I don't know what the shape of this is yet. Sure, they did tell me it's a square, but I don't know that quite yet. Not until I take this slice and I push it over. And when I push the slice over, no, it's not a CD, it's not round. Turns out that when this slice falls over, it's a square. Now the key here is for me to find the area of this square. If I can find the area of this square, I'm in good shape. So let's see, what do I know? Well, I know that the radius of this circle, if I draw a radius from the center out to the edge of my slice, I know that radius is 3. I don't know this dimension right here. I'm going to call that x. And I don't know this dimension right here, but I'll call that y. And so I've got myself a little triangle here, and I know that x squared plus y squared is equal to 9, but that's about all I know. You know what else I know? I know that this square has a side right here that's y. And down here, since this is a circle and I've centered this at the origin, that's got to be a y down there. You know what? This is 2y on each side. The square, they're all the same. I know that the area of this is 4y squared. However, what we learned when we were finding the areas in section 5.1 is if you make a slice, and we have made a slice here, when you make a slice that hits the x-axis, everything needs to be in terms of x. And so I've got an area, but it's in terms of the wrong variable. We're going to find that that happens a lot. Let's come back down here. Let's come back down here and let's see what's going on down here. Let's see. I'd like to know what y squared is in terms of x's. So I know that y squared is 9 minus x squared. So if I want my area in terms of x's, I'm going to say that the area is equal to 4 y squared. 4 times 9 minus x squared. I know that the area is 36 minus 4x squared. That's the area of my square in terms of x's. And I know volume is equal to the integral from a to b of the area, in this case in terms of x's, times the thickness of each slice. So in our case, the volume is equal to, well, where does this figure begin? Where is the beginning of the x's? I think we'd agree that that begins at -3 and goes all the way to +3. What is the area in terms of x's? 36 minus 4x squared. That's the area times the thickness, which is some very small change in x. And once we set up the integral, it's calculated. So you grab your calculator, maybe press pause, see what you come up with, and then compare it with my answer. I believe the answer should be 144. If not, let me know and also fill me in on where I made a mistake. Let's take a look at another one. Now we've got the same figure. We've got a solid with a circular base, radius 3. And drawing the top view of this is always going to be important. I'm going to encourage you to do that all the time. And cross sections perpendicular to the x, so I'm going to slice like this again. So everything better be in terms of x because my slice hit the x-axis. I'm going to pull that slice out over here. I'm again interested in what this thing looks like. So I'm going to push it over. And when I do, I get an equilateral triangle. All three sides of this guy are the same. Now, you might be wondering, how do I find the area of an equilateral triangle? And that involves knowledge of 30, 60, 90 triangles, which you had back in geometry. And what we could prove, and I'm just going to give it to you, but what we could prove is that the area of an equilateral triangle is equal to the side squared times the square root of 3 divided by 4. That's the area of an equilateral triangle. Again, using rules of 30, 60, 90, each one of these angles is 60 degrees. And if we drew an altitude in here, we'd have a couple of 30, 60, 90s. And this is the area we would come up with. All right, well, that's really nice. And I do know how long this thing is. Again, this is y. Again, this is y. So this is 2y. And so the area of this equilateral triangle is equal to 2y, which needs to be squared, times the square root of 3 divided by 4. And if you're wondering, hey, is this formula for an equilateral triangle something I need to memorize? Yeah, it kind of is. If I multiply this out, I've got 4y squared, square root of 3, divided by 4. And so the area of this triangle is y squared times the square root of 3. But again, we need everything in terms of x because the slice hit the x-axis. So again, I'm going to draw this radius, a radius of 3. I'm going to call this distance x. And again, x squared plus y squared is equal to 9. And so y squared can be replaced, or I can substitute a 9 minus x squared in the place of y squared. So my area in terms of the correct variable is 9 minus x squared times the square root of 3. Volume. Volume by cross-section. Now again, everything's in terms of x, and x's begin at negative 3. X's end at positive 3. And now I need my area times my thickness. And the area is 9 minus x squared times the square root of 3. And I could have written that square root of 3 out front if I wanted to, because it is a constant that I'm multiplying by. Thickness. And so the drawing and the integral, as you get assessed on this stuff, either by me or by AP, being able to make the drawing to help you set up that integral, those are going to be worth something, especially the. Now, put this into your calculator, maybe press pause, and we'll compare answers. I believe I've done this correctly. That's the volume you're going to get. All right, let's take a look at another one. But this one, the base of a solid is a triangular region, so it's not circular anymore. Bounded by the x-axis, the y-axis, and this line, y equals negative 1/2 x plus 2. Again, cross sections perpendicular to the x, but this time they are isosceles triangles. Two sides are the same, with one leg on the base. So let's draw this. And I'm going to draw this figure here. Y equals negative 1/2 x plus 2. Now I know that that's got a y-intercept of 2. I know it's got the slope of negative 1/2. So it would look something like this. And I think it's got a slope of negative 1/2. I think that means it's going to hit out here at 4. I think that is a slope of negative 1/2. So we've got the region bounded by the y-axis and the x-axis. We've got that triangular region right there. And we're going to take cross sections perpendicular to the x-axis. So everything's in terms of x. I take my cross section out here, I just pick it up and stand it on edge. Then I'm going to push it over. And when I do, I get an isosceles triangle. Where these two sides are the same. It's an isosceles right triangle. I put the word in there, so if you'd add that, I'd appreciate it. Well, again, this is some y measurement here. This distance right here is some y measurement, and so is this because it's isosceles. So what's the area of an isosceles triangle? Well, base times height divided by 2, or 1/2 the base times the height. Again, wrong variable. What's the relationship between x and y in this one? It's not x squared plus y squared is 9. Here is our relationship between x and y. The area is equal to 1/2 y squared. 1/2 negative 1/2 x plus 2 squared. I've got my area and I've got it in terms of the correct variable. So the volume is equal to, now I'm going to leave a suspicious space before an integral. And everything's in terms of x's. So where do the x's start in this figure? Where do the x's end in this figure? As I write my area, and I pull that 1/2 out front, and I've got an area of 1/2, negative 1/2 x plus 2 squared. Got to multiply that by my thickness and add an infinite number of those volumes together. So press pause. Calculator time. And I'm thinking, that's a volume. All right, let's try one more. We aren't going to do the last slide, but we'll do example 4. I hate semicircles, but they exist, and so we're going to do this one. We've got the exact same shape we just had. And again, making the drawing the top view of this thing, so we have an idea of what the shape looks like, and therefore how to find the area of that shape. So same triangular region that hits out here at 4, starts over here at 0. But now when we take cross sections, now when we take this cross section, and I'm going to draw it a little bit bigger. Okay, this is a magnified view of it. Take this cross section standing on its edge. Let's push this guy over. And now when I push it over, I get a semicircle. And this thing right here, that's the diameter. So again, I've magnified this. Those are the same thing. That was what was resting on my table. And I pulled it out of there and I pushed it over. Well, okay, now I've got a semicircle. So put the center of that semicircle right there. And this distance right here was y. So that means this whole distance here needs to be considered y. And so this radius is half of a y, because to find the area of a semicircle, well, we need radius, don't we? The area of a semicircle is pi r squared divided by 2. So I've got to take pi. I've got to take my radius of 1/2 of a y. I've got to square that, and I've got to divide by 2. That's pi. 1/4 y squared divided by 2. Or instead of dividing by 2, maybe I could multiply by 1/2. So the area is 1/8 y squared. Well, again, wrong variable. Here's the relationship that turns y's into x's. When I slice hit the x-axis, everything needs to be in terms of x's. And so the volume of this three-dimensional figure, which starts at an x value of 0 and ends at an x value of 4. The volume is going to be 1/8, but instead of y squared, negative 1/2 x plus 2 squared times the thickness of each slice. And with the assistance of our calculator, we add an infinite number of these guys together. Now, if I've keyed it into my calculator correctly, and if you do, well, we'll agree on the same answer. I believe and let me know if I'm somehow keyed that in incorrectly. All right, that is volume by cross sections, where cross sections are going to be squares, triangles, semicircles. Our next section is going to be the exact same thing, but all of our cross sections are going to be either circles or they're going to be circles with a hole in them called a washer. But we'll eventually get to that. Let's get some practice on volume by cross sections using squares and triangles and semicircles. So check out Schoology for the assignment, and good luck.